Industry is working around the clock to produce the goods and services we use every day. To stay in business, the companies providing these goods and services must produce them as safely and efficiently as possible. And of course, their products must have consistent high quality. Modern industries rely on the ability to measure and control dozens of variables that not only govern product quality, but also ensure maximum plant safety and efficiency. All major industries, from the automotive and aerospace to the food and drug industries, depend on precise and reliable control systems. The methods of production and types of equipment vary greatly from one industry to another. The drug industry must maintain rigid quality control to produce pure and safe products. A nuclear power plant must not only provide a very reliable source of electricity, it must also pay particular attention to plant safety. So must a steel mill. The product of a paper mill bears little similarity to that of a power plant or a steel mill, but quality and efficiency are just as important. The chemical and petroleum industries each have scores of different processes with rigid specifications for each product requiring accurate control of many variables. In all of these industries, whether the plant is small or large, the measurement and control of the manufacturing variables is the key to successful operations. The systems controlling these variables are known as automatic control systems. They can vary greatly in complexity, from small and simple systems to large and complex systems that monitor and control hundreds of variables in larger plants. The controlled variables might include the position of a robotic arm welding pieces of a car body together, the flow of air past fabric in a hot air dryer, or the amount of chocolate in a cookie. Many types of instruments and controllers are available for a variety of industrial processes. Even though control systems vary from pneumatic to electrical to digital, the same basic control concepts apply, regardless of the industry, variables controlled, or control technology. To illustrate the different types of controls commonly used, let's consider a small chemical company that eventually grew to become a large and very profitable operation. Its principal product was a specially blended liquid, which was shipped and sold in bottles. In the early days of the company, the manufacturing process was quite simple. The product was made one batch at a time. Bulk materials and liquids were combined in a large tank and agitated. They were then heated with steam to 80 degrees to ensure proper blending of all the ingredients. Consistent blending was essential to this process. If, for some reason, the temperature rose above 85 degrees, one of the ingredients would become overactive and the product would be off-spec. On the other hand, if the batch were allowed to cool below 75 degrees, the blending was incomplete and the product had to be reprocessed or thrown out. In short, good product quality required that the temperature be maintained within plus or minus 5 degrees. The temperature control system was similar to a simple thermostat with an automatic valve that regulated the flow of steam to the jacket surrounding the tank. The controller received a signal from a temperature sensor in the product. A sensor is a device that measures the value in question, in this case, temperature. The sensor was electrically connected to an indicator, and the product temperature was shown on a graduated scale similar to an ordinary thermometer. When the temperature increased, the red indicator moved upward. When the temperature decreased, the indicator moved downward. The desired operating temperature, or set point, was selected by setting another indicator, the green one on the left of the scale. This setting established the position of an electrical contact within the controller, and with the closing of this contact, the automatic steam valve was caused to open. Here's how the control system operated. The desired blending temperature was 80 degrees, so the set point was moved to that value. At startup, the batch was cool. The electric contact within the instrument was closed, so the automatic steam valve was open, and it permitted steam to enter the jacket surrounding the tank. As the batch heated, the red indicator moved upward until it reached the set point temperature. When it got there, the electric contact within the controller opened, causing the automatic steam valve to close. Note that the batch temperature rose slightly above 80 degrees due to steam trapped within the jacket. As the batch cooled, the indicator moved downward until the control contact closed and the automatic valve returned to the open position. The heating cycle then repeated. Here is a continuous record of the temperature. Time has been speeded up, and the cycle we see here is many times faster than that of the actual process. Note that the variations are well within the limits of plus or minus 5 degrees. The quality of the product was excellent, and using this simplest type of controller, the on-off controller, the plant could repeat this operation day after day. However, the sales of the company's product continued to increase, and soon it added more blending tanks. In this manner, it grew and grew until there was no space left for additional tanks. The plant manager began to think he might have more room to work if he moved his desk into the phone booth outside. And the plant's maximum output, despite its best efforts, was only 2,000 bottles a day. One day, its best customer offered the company a long-term contract that would require the company to guarantee an output of 5,000 bottles a day. This was a critical situation because there was no surrounding property on which to expand. However, no enterprising business can afford to pass up a contract like that. As it set about planning for increased production, its first big problem was to determine the most economical type of expansion. Two schemes were proposed. First, the company could build a completely new and larger plant in another location, but this would be a lengthy and costly undertaking. Or it could remodel part of its existing building and install a continuous process, one that would blend the solution in a continuous manner and deliver it to two fully automatic bottling machines. This process could produce better than 5,000 bottles a day, and the increase in production would quickly pay off the more modest investment in new machinery required. It was obvious that the continuous system was the best way to increase production. This was the general plan for the new process. Raw materials would flow into the top, and their rate of flow would be accurately controlled. A motor-driven agitator would provide rough blending of the raw materials, but for the final blending, the product would flow through a heat exchanger where it would be heated to 80 degrees. The blended product would then flow through a pipeline to two automatic bottling machines. To control the temperature, the plant engineers installed one of the on-off controllers previously used on a batch blending tank and added a new, larger valve to regulate steam input to the heat exchanger. They soon found out, however, that their selection of a controller was a poor one. When the installation was complete and the process was started, they realized that the metering of the raw materials was highly successful. The mechanical mixing was better than expected. The heat exchanger performed admirably, and the controller opened and closed the new steam valve. But look what happened to the temperature record. The temperature would first increase to 90 degrees and then fall to 70 degrees. This cyclic condition continued hour after hour, and the finished product, because of improper blending, was worthless. The engineers were dismayed, but not as much as the plant manager or his boss, the president of the company. Why did the old batch process work so well and the expensive new continuous system consistently turn out substandard product? To answer this, we need to compare the dynamic behavior of each. The batch process was a large tank of liquid, and when the steam valve was opened, the temperature changed very slowly. As a simple analogy, consider a bathtub full of water. The hot water can be turned on and off, but the temperature of the water in the tub changes only slightly. The bather is quite comfortable in spite of the on-off control action. The continuous process behaved in a different manner. The rate of heating was rapid, and there was no large mass of liquid to absorb the change from valve opened to valve closed. This we can compare to a shower. When the hot water valve is fully opened, the product, or a bather, feels the change immediately. When the valve is closed, the product is in trouble again. As the cycle repeats, the product continues to suffer because of the on-off control action. It is obvious that in this case, on-off action just doesn't work. Now, if the valve were slowly adjusted until just the right amount of steam was admitted to the process, the temperature could be held within the desired limits. This adjustment of valve position was clearly needed in the continuous process. Let's take a look at a controller called a proportional controller that provides valve adjustment proportional to the measured value of the process, in this case, temperature. The red and green indicators are similar to those in the on-off model, but a third indicator has been added to show valve position. When the temperature is high, the controller causes the valve to close. When the temperature is low, the controller causes the valve to open. As the temperature slowly rises, the valve gradually closes. The controller provides the necessary adjustment through proportional action. To demonstrate the principle of proportional action, let's use a balanced beam to show how valve position can be made proportional to the measured temperature. The controller, of course, does not use a beam like this, but its action follows the same principle. This type of action is called proportional action. A change of temperature causes the valve to open or close in such a way that the valve position is proportional to the measured temperature. If the temperature is very low, the valve is fully open. As the temperature rises, the valve will close gradually and reduce the input of steam to the process. This action will continue until the valve delivers just the right amount of steam to maintain a constant temperature. In this example, when the valve is 50% open, the input of steam will maintain the process at 80 degrees. Any change of temperature will cause the valve to open or close in proportion to the size of that change. If we want to adjust the amount of proportional action, we can move the pivot point to a new position. When we move the pivot to the right, a small temperature change causes a large valve movement. This is called high gain. If we move the pivot to the left, a large temperature change causes a small valve movement. This is called low gain. Let's return to the proportional controller and see how its action matches that of the balanced beam. The amount of proportional action can be changed by adjusting the dial marked gain. With a high gain setting, a small temperature change causes a large output change. This amplification of the temperature change could cause the valve to move through its entire range from fully open to fully closed. On the other hand, with a low gain setting, the output change is small and the valve is moved only a small amount. Now let's look at the operating parts of the controller in the form of a block diagram. The measurement, in this case temperature, moves the red indicator. The set point, or green indicator, is adjusted manually to some desired setting, such as 80 degrees. Any difference between these values, as shown by the two indicators, is detected by a circuit controller known as the error detector, or comparator. If the temperature is below the set point, a negative error signal, E, is generated. If the temperature is above the set point, a positive error signal is generated. The value of the error signal, either plus or minus, is sent to the proportional unit. Here, it is modified according to the gain setting to provide an output signal that adjusts the valve opening. The blue indicator within the controller shows the position of the valve, and the scale is graduated from valve closed to valve open. This allows us to observe the position of the valve whenever we want to determine the amount of steam entering the system. However, let's get back to our story of the continuous process used by our growing chemical company. The on-off device used in the batch process was replaced with the proportional controller. When the process was put into operation, the solution was cooled, and the controller called for full valve opening. The inrush of steam caused the temperature to increase, but as it rose, the proportional action caused the valve to gradually reduce the amount of steam to the heat exchanger. This, in turn, slowed down the rate of rise. Soon, the temperature reached 80 degrees. The valve admitted the correct amount of steam to satisfy the heating requirement, and the plant was able to hold the product temperature within the correct limits. To get this performance, the engineers found that a gain setting of 1 was required. When the gain was higher than 1, The process cycled at temperature extremes nearly as great as those with the on-off controller. On the other hand, when the gain was set lower than 1, the control action was sluggish, and a large amount of product was lost during startup. Experience indicated that there was an optimum gain setting for this type of process. Nevertheless, there were more troubles just around the corner. The proportional action controller did a good job when the plant operated just one bottling machine. When the second bottling machine was started, however, something unexpected happened. Now the flow through the heat exchanger was doubled, but the control valve at that time was admitting only enough steam for one machine. Therefore, the product temperature dropped. The proportional controller sensed this change and opened the valve gradually and continued to open the valve until the temperature leveled off. But even then, the product temperature was below the lower limit. This condition is called offset from the desired set point and is caused by a load change on the process. Let's look at another example to see how such an offset occurs in a proportionally controlled process. Here we have a large tank out of which water flows continuously. At the same time, fresh water flows into the tank, and the water level is controlled with the aid of a float. If the outflow from the tank increases, the water level drops, thus opening the valve for greater inflow. The more the water level drops, the more the inflow valve opens to compensate. Likewise, if the outflow is reduced, the water level rises and causes the inflow valve to close. But look what happens when someone opens the outflow tap so water leaves the tank in greater volume, representing a large load change. The water level drops by a large amount, causing the inflow valve to open wider. The valve will have to open wide enough so that the new inflow of water equals the new outflow. Once this occurs, the water level will stay constant. But in order for the inflow valve to be opened wide enough, the float must be lower in the tank. In other words, the water level has been offset. It is clear then that in the event of a large load change, proportional action simply isn't enough. Similarly, in the chemical plant, proportional action alone was not adequate to return the temperature to the set point during load changes. An additional control action was needed, one that would open the valve beyond that of proportional action whenever the second bottler was turned on. It should also work in the opposite direction whenever one of the bottling machines was turned off, say for cleaning. To accomplish this, it was necessary to add another feature to the controller. This feature is known as integral or reset action. An integral unit responds to the error signal of the system, just as the proportional unit does, but with an important difference. The proportional unit is concerned only with the size of the error, but the integral unit is concerned with the duration of the error as well. In effect, it monitors the average error over a period of time. In this way, when the system experiences a load change, the integral unit will detect that the error, although constant, is still present after some time. It will then move the action of the proportional unit to correct the error or offset. Because of its ability to return a system to its set point, integral action is called reset action. In effect, the integral unit makes frequent checks on the performance of the proportional unit. If it finds there is an offset, it shifts or resets the proportional control action to eliminate the offset. The frequency with which the integral unit resets the proportional unit can be adjusted. This frequency is expressed as repeats per minute or minutes per repeat. Reset control, then, is a function of the time of deviation. In the case of the chemical plant, when the second bottling machine started up, the additional load caused the temperature to drop. Proportional action caused the valve to open in proportion to the temperature change. But in addition, the integral unit also responded to the error signal. The output of the controller slowly increased as long as the error signal was present. This increase in controller output caused by the combination of proportional and integral action caused additional valve opening. This allowed the temperature to return to the set point. Once that happened, the error signal became zero, and the integral action stopped. The steam control valve was then in the correct position to maintain the process temperature at its set point. In effect, the valve position had been reset by the integral action. Later, when one of the bottling machines was shut down, the combination of proportional and integral action continued to reposition the valve until the temperature returned to the set point. The valve once again delivered the right amount of steam for the system. To obtain this performance, the plant engineers found that a proportional gain of 0.7 and an integral or reset rate of 1 were optimum settings. Higher gain and faster integral values caused the process to become unstable. Lower values were too slow for good performance. The company was pleased that the new two-mode controller solved the problem of load changes. But the production foreman, the person responsible for product quality, pointed out that every time the second machine was started or stopped, there was a large temporary deviation, during which about 50 bottles were off standard and had to be thrown out. The sudden load changes were causing the trouble. Slower and smaller load changes caused no such difficulty. It became obvious that the controller did not move the valve fast enough to prevent overpeaking during load changes. If the controller could detect the rate of temperature change and could cause additional valve movement whenever the temperature changed rapidly, overpeaking could be greatly reduced. What was needed was a device that could anticipate overpeaking based on a rapidly increasing or decreasing error signal. Such a device is called a derivative unit, or because it is based on the rate of change of the error signal, it is often called a rate action unit. To explain its operation, suppose that a device similar to an automobile speedometer is attached to the temperature measurement indicator, and the speed of movement is shown by a needle on a dial. When the temperature changes slowly, a low value is shown, and when the temperature changes rapidly, a high value is shown. When the temperature is constant, that is, when it stops changing, the needle goes to 0. The derivative action unit acts like it contains the speedometer. When the needle indicates a fast temperature change, it adds a signal to that of the proportional unit, so additional valve motion results. But when the temperature is steady and the needle is at 0, the derivative action stops. Let's see how this extra valve movement comes about in the chemical plant. When a load change occurs, the temperature drops rapidly. The derivative unit immediately acts along with the proportional unit to produce additional valve movement temporarily. As the temperature levels off, the derivative action decreases. Once the temperature stops changing, the valve returns to the position dictated by proportional and integral action. The additional valve motion caused by the derivative or rate action unit is very good at reducing or eliminating overpeaking. The amount of rate action can be adjusted to suit the process in question. If the rate action is too fast, the process will become unstable. If it is too slow, the controller will be governed by proportional and integral response only and will cause overpeaking. The instrument now contains 3 modes of control. Proportional action with adjustable gain to maintain the system under most conditions. Integral or reset action to compensate for load changes. And derivative or rate action to speed up valve action when rapid load changes occur. Now let's see how the chemical plant performed while taking advantage of this 3-mode controller. With one bottling machine in operation, very satisfactory control was obtained. When the second machine was started, note that some deviation took place. The valve was temporarily opened to allow a large inflow of steam, and the temperature did not drop below the limit for good product. When the second machine was shut down, the reverse action took place. The valve was temporarily closed, and temperature did not exceed the upper limit. The control instrument was therefore in full command of the process. The plant could operate at peak performance day after day with no waste. In our brief and simplified story, we have talked only of the measurement and control of temperature. Similar control systems are used to control other variables, such as flow, pressure, level